So this lesson is on how derivatives affect the shape of a graph. So when we talk about a derivative being positive, we know that the slope of the tangent line is positive. So the function is increasing, or if the slope of the tangent line is negative, we know that the function might be decreasing. So let's go through some theorems first. So if we take a derivative and we know that that derivative is positive on some interval, then we know that the function is increasing. So you can see the derivative at that point here is positive, but I can see on my blue function, the blue function is increasing at that sort of vicinity. If my derivative is less than 0 on an interval, then the function is decreasing on that interval. So let's just take an example and figure out how to figure out where the function is increasing and decreasing. So here they give me a function. It's a quartic function. So I'm going to take the derivative of the function, 12x cubed minus 12x squared minus 12. I want to set this derivative equal to 0, because those are going to be the points where the derivative is equal to 0, and then, in between those points I can figure out if the derivative was positive or negative. I'm going to factor out a 12. Oops, and I can see I missed a term here, so the derivative of 12x squared is minus 24x plus 5. So I factor out a 12, I get, or I'll actually factor out a 12x. I'll get x squared minus x minus 2. And then I'm ready to factor. So 12x. I need two numbers to multiply to negative 2 and add to negative 1. So x minus 2, x plus 1. So I want to find out where the zeros of the derivative function are. So there's an x-intercept at 0, 2, and negative 1 on the derivative graph. So what I'm going to do is I'm going to draw a number line, and this number line represents the values of f prime of x. I know that f prime of x is negative 1, 0, and 2. When x is those values, the f prime of x is 0. So I'm going to kind of write myself a little note that at these values, the derivative was 0, 0, 0. And then I want to take a point in each section to figure out, is the derivative positive or negative? So let's say I take a point x equals negative 2. If I sub it into my simplified derivative, minus 2 minus 2 minus 2 plus 1. So that's going to be negative, 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 which the result is negative. If I take a point in this section, say x equals negative 0.5, this would be 12. This would be a negative, negative, positive. So the overall result here would be positive. So I'm taking that value and subbing it into this simplified derivative right there. Let's take a point in this section, say x is equal to 1. I plug it in, I'm going to get 12 times a positive value times a negative value. 1 minus 2 is negative 1. 1 plus 1 is 2, so that's a positive value. So this overall result is negative. And finally, if I do x is equal to 3, I get 12 times 3, which is positive, 3 minus 2, which is positive, and 3 plus 1, which is positive. So the overall result is positive. So based on this theorem that we have above, if my derivative is greater than 0 on the interval, we say that the function is increasing. If the derivative is less than 0, the function is decreasing. So here, over here, because my derivative was positive, I know in this section of my graph the function's increasing. This section is decreasing. This section is increasing. This section is decreasing. And I want to summarize my answer with a sentence. So f of x is increasing on the interval -1 to 0. I don't want to include -1 or 0 because at those points the derivative is exactly 0. Union 2 to infinity. And the reason that it's increasing is because the derivative was positive at these values in those intervals. F of x is decreasing on my interval where the derivative is negative, so -infinity to -1 union, and then I have another negative here, so 0 to 2, because f prime of x is less than 0. So we're literally finding the derivative, setting that derivative equal to 0 to find what we call the critical points or critical numbers. If the derivative is undefined or we have vertical asymptotes, we want to also represent that on our number line. And then we want to test the signs in each section and then figure out, is the function increasing or decreasing based on the sign of the derivative. So all the stuff that I've written in orange here represents the value of the derivative, whether it's positive or negative. Okay, find the open intervals, so they're going to be always open, where the function is increasing or decreasing. I know that relates to my first derivative. So I take my first derivative, 3x squared minus 3x. I'm going to bring down the 2x, and then you'll see that the 2's will cancel out. So I factor out a 3x, and I'm left with x minus 1. And so my simplified derivative is 3x, x minus 1. I want to find where my derivative is equal to 0 or does not exist, because that's sections where my derivative graph will be broken up. This would be when x is 0 or x is equal to 1. I set a number line with values to represent my derivative graph, and I want to know whether these values are positive or negative. So what I'm going to do is I'm going to take a point in this region, say x is equal to -1. I sub it into my derivative simplified. This will be -3 times -2, which is +6. So I'm just going to write a positive sign. It's not so important the value of the number. What's more important is just the sign. So when I do these other ones, you're going to see I'm going to take some shortcuts. So this is going to be 3 times +0.5, which is positive. Positive 0.5 minus 1 is negative, so positive times negative is negative. When x is equal to 2, just remember I'm subbing it into this simplified function. 3 times 2 is 6, which is positive. 2 minus 1 is 1, which is positive, so my overall result is positive. Now I'm going to make a conclusion about what does that tell me about the original function. Positive derivative means original function is increasing. Derivative being negative means that the original function is decreasing. Positive, we mean increasing. And then we just say that f of x is increasing on -infinity to 0. If you have more than one interval, you combine it with a union symbol. And then the next interval would be 1 to infinity. And we can write because f prime of x is greater than 0. F of x is decreasing on 0 to 1 because f prime of x is less than 0. And that would be my final answer for that part. So what we're going to do is build into what the derivative helps us to say about an original function. This is sort of the first big thing you need to know, is when is a function increasing or decreasing. Increasing means that the function is kind of going up in that format or that format. Decreasing means the function's kind of facing down or decreasing over time and going kind of either curved downwards, but the slope trend is negative. So now the first derivative test, this is going to help us identify whether we have local maxes or local mins. So if my derivative changes from positive to negative, that kind of visually looks like a positive slope to a negative slope. We can see that the function is going to have a local maximum. If my derivative changes from negative to positive, then we say that the function has a local minimum. And if it doesn't change signs, then we have no max or no min. So you can look at these diagrams here. If my derivative is less than 0 on this half of the graph, and then all of a sudden it switches to being positive on this half of the graph, my derivative's gone from negative to positive. So we say that there is a local minimum or a relative minimum. You can use the word local or relative. You can see here that the sign changes from positive to negative. So there's a local maximum or a relative maximum. You can see here that the sign went from positive to positive because I have a positive slope and then another positive slope. So there's nothing happening. Or I can have a change in slope from negative to negative and nothing's happening. Okay, so that's the next sort of theorem we're going to add into the mix. So in a given question, I would say, here's a function. Find me where the function is increasing and decreasing and whether the function has local maxes or mins at certain x coordinates. So here, find the local max and minimum values of the function. So it requires us to take a derivative. Now over here, you can see that they've sort of given us the extreme value theorem as well, because they've given us a continuous function on a closed interval. So we could think extreme value theorem, but they're asking us local and not absolute. And this kind of gives us the absolute max and min on a closed interval. So we're not really referring to extreme value theorem. We're just referring to the theorems that were above. So my derivative is 1 plus derivative of sine x is cos x, and I'm going to keep my interval from 0 to 2 pi. The reason I'm keeping that interval is that's the domain they want me to work on. I'm going to take my derivative, set it equal to 0, and you're going to see some trig coming in now. 1 plus 2 cos x equals 0. Cos x, if I isolate it, would be negative 1/2. And I need to solve where does cos x equal negative 1/2. So first I need my reference angle in radians. So the reference angle for where does cosine equal 1/2, you can use your finger trick or your hand trick or your unit circle. So you'll know that at pi over 3, which is 60 degrees, the cosine value is 1/2. Second of all, we're going to do our cast rule to figure out what quadrants is cosine going to be negative in. There'll be negative here and here. And my step 3 is to find my actual rotational angles. So x would equal, 2 pi over 3 for quadrant 2, because it's pi minus pi over 3. So that's back to your 30-1, and x has equals 4 pi over 3, which is pi plus pi over 3, and that's our quadrant 3 answer. So these are my two answers in one rotation of the unit circle. So on my number line, we're going to stop our interval at 0, and we're going to stop our interval at 2 pi. We don't want to consider anything before that. I throw my critical points on here, so 2 pi over 3 and 4 pi over 3, and I need to figure out, is my value of the derivative positive or negative in these intervals? So let's test that out. So let's test this one, so x equals, now 0 to 2 pi over 3 is something between 0 and 120 degrees. So think of a value that's nice to work with. So maybe 90 degrees. So I'm going to make you think of 90 degrees, but we need to make sure everything stays in radians. So 90 degrees is pi over 2. Cosine of pi over 2 is 0. So the value would be 1. So my sign is positive here. 4 pi over 3 is 240 degrees. So think of a value that's nice in between there. So I'm going to go to 180 degrees. So x will equal pi. So cos of pi is negative 1. 1 plus 2 times negative 1 will give me a negative result. And then we know that 2 pi is 360 degrees. So again, you can refer to that. If I take a nice value like, I don't know, 3 pi over 2, which is 270 degrees. And then cosine of that is 0. So again, we're back to being positive. Okay. So now I can say, let's use another color here. This is sort of, so g of x here would be increasing, decreasing, increasing. So we know that the graph is kind of going up and then down and then back up. So if I needed to make a conclusion on what's happening right at this value, we can sort of see it swinging like that. So there's a local max at x equals 2 pi over 3. And then over here we have a local minimum because it's going down and then up. Minimum at x equals 4 pi over 3. Now let's say I wanted the actual y coordinates for these points. Now that would just require me to sub these values back into the original function. So when x is 2 pi over 3, y is 2 pi over 3 plus 2 sine of 2 pi over 3. And then you can kind of simplify that answer out. So 2 pi over 3 plus 2. Sine of 2 pi over 3 is root 3 over 2. And positive because that's quadrant 2. So 2 pi over 3 plus root 3 would be the y coordinate. This would represent my local max. And then my local min would be represented by x is equal to 4 pi over 3. I sub that into my original function to get the y coordinate. 4 pi over 3 has a reference angle of 60 degrees, but in quadrant 3 that would be negative. So this would be 2 negative root 3 over 2. And then y is equal to 4 pi over 3 plus. And then that's my y coordinate, 4 pi over 3 minus root 3. And there's my local max. Or sorry, my local min. So now basically we're going to go through, find the local maxes and mins of this function, find the local maxes and mins of this function in the same format. So let's go ahead and work out these examples. We take the derivative of the function. This one is chain rule, so 2/3 x squared minus 4. Subtract 1 from the exponent, and then chain rule says multiply by the derivative of the inside. My simplified answer would be 4x sits on the numerator, the 3 and the cube root of x squared minus 4 sits on the denominator, and that's my simplified derivative. I find where is the derivative equal to 0, which is me setting my numerator equal to 0. So that would mean x is 0. You also ask yourself, where is the function undefined, does not exist? That would be when x squared minus 4 in the cube root is equal to 0. So that tells me x is equal to plus or minus 2. So those are my critical values. I'm going to put those critical values on a number line. So 0, minus 2, plus 2. We put my derivative there. So now what I'm going to do is I'm going to kind of do this a little bit quicker, and we're going to go through it a little bit faster. So I take a value like x equals -3 for this section. I sub it into my simplified derivative. So the numerator will give me -3. So that would be a negative, I'll just do it up here, divided by -3 squared is 9 minus 4 is positive. So negative over positive, which means the overall result is negative and my function is decreasing. When x is equal to -1, the numerator is negative. The denominator is also negative. Cube root of a negative is negative. This would be positive and this would be increasing. When x is equal to positive 1, I'm going to get a positive over a negative, which will be negative. That means decreasing. And positive divided by positive will give me a positive result, which means the function is increasing. So I'm taking test values and subbing it in there and determining if the value is positive or negative. If I'm going a little bit too quickly there, then basically you just slow yourself down, sub it in very carefully. Practice subbing it in without using a graphing calculator, because I would expect that on an assessment. And then now we can say local max at, so this is going down and up, so that's a min. Up and down is a max, so local max at 0. When x is 0, I sub it into my original function to get the y coordinate. And then it goes positive to negative, so we can say because derivative changes from positive to negative. And then we have two local minimums, so local min at, this is going that way, at -2 and +2. And to find the y coordinates, we take in, sub it in the original function. You're going to notice that that will give me 0. 2 squared is 4. 4 minus 4 is 0. 0 to the power of 2/3 stays 0. And we can write because f prime changes from negative to positive. When you're describing your solutions, please describe it like I've presented here too. Tell me where the location of the max or min is, and then tell me why it is a local max or min using the first derivative test. Example 5, same idea, just it requires you to be able to take a derivative, simplify the derivative, and work from there. So f prime of x, this time we're using quotient rule, derivative of the top times the bottom, minus, leave the top the same, derivative of the bottom over the bottom squared. Now, before we go to simplify this, watch to make your simplification easier. There's an x and x term in every expression. So I'm going to divide top and bottom by x, which means I'm going to get 4x to the 4 minus x to the 4 plus 1 times 2, because that other x will cancel. All of this stuff is part of one term, and my bottom will be x cubed. And now I'm just going to simplify this up. So 4x to the 4th minus 2x to the 4th will give me 2x to the 4th minus 2 divided by x cubed. And one more cleanup step, factor out the 2 and then do difference of squares. You're going to get x squared minus 1, x squared plus 1 over x cubed. And then one more difference of squares step, x minus 1, x plus 1. Let's move that over. I'm going to run out of space. So 2x minus 1, x plus 1 is the difference of squares. And then the other term stays positive over x cubed. So if I've done my derivative correctly, I'm going to set my derivative equal to 0 and undefined. F prime of x equals 0 means that my numerator is giving me a 1 and a negative 1. F prime of x being a does not exist means that x equals 0. You're going to notice that x equals 0. It is not in the domain of the function. It's actually a vertical asymptote. If I sub in 0 into the original function, I'm going to get 0 to the 4th plus 1, which is number over 0. So it's almost like the number over 0 type. So it's the vertical asymptote type, not the POD type. So now when I draw my number line, I have my derivative. This expression here is where I'm subbing values into. So I put 0 on my number line, but underneath I'm going to label it as a vertical asymptote. A vertical asymptote cannot be labeled as a max or a min because it's a vertical asymptote. So we're going to take values and sub them in. So I'm going to take x is equal to minus 2, sub it into my simplified derivative. So positive, negative, negative 2 plus 1 is negative, negative 2 squared plus 1 is positive, divided by a negative. The overall result is negative for the derivative. When I take a number like negative 0.5, 2 is positive, negative 0.5 minus 1 is negative, negative 0.5 plus 1 is positive, the last term is always positive, and the denominator is a negative cubed, so overall result is a positive sign. When x is 0.5, I get positive 2, half minus 1 is a negative, half plus 1 is positive, last term is squared plus 1 is positive, and the bottom is going to be positive, so the overall result is negative. And when x is equal to 5, we're going to get an overall positive result, which is positive. We have to remind ourselves, what does that say about the original function? Decreasing, increasing, decreasing, increasing. Now, decreasing to increasing is kind of like this. Local min, local min. This is a vertical asymptote, so it can't be classified as anything. So I'm going to say local min at -1 and a y-coordinate. So when I sub that into my original function, -1 to the 4th plus 1 over 1. And there's a local min at +1, which is going to give me the same result, 1 to the 4th plus 1 over 1, because the derivative changes from negative to positive. In the next video, I will show you how to do concavity, which relates to the second derivative, and then we're going to focus on the second